an HD family connection and raises funds all over Canada for HD research as well. So I'm very pleased to welcome Dr. Tamara Maiuri.
Thanks, Matt. Thank you again, all of you, for participating in this awesome event year after year. It really has been a wonderful time. So thanks, Matt, for the invite. And I've had so much fun and met so many awesome people. And I'm really excited to tell you a little bit about where your money goes when you raise all this money through events like these. So I just wanted to start with a couple of numbers. This little infographic was put out by the Huntington Society last year, and it's the stats for 2017. So if you look on the right of the screen, you'll see 1.3 million raised for research purposes by 150 leadership volunteers. So, you know, your group is small but mighty, and it's a small but mighty group working across Canada to raise these funds. It's actually incredible. So let's talk a little bit about how that money goes from, you know, little observations and little just trying to figure things out, and really does come to breakthroughs in the end. What I usually like to do is start with a little family history, just to put everything in perspective and remember why you're all here and why we're all working so hard on this. So I hope you can see these pictures. On the far left is a picture of my great-grandma Pearl and my great-grandfather and two of their 4 kids. One of their 4 kids was my grandfather, pictured in the middle, Victor. That was my mom's dad. And unfortunately, my great-grandfather had the HD gene and passed it on to all 4 of his kids. So, as Mac mentioned, it's 50-50 chance for each kid, and my grandfather and his siblings were all the unlucky half of the 50-50. On the right, you can see a picture of me with my great-grandma Pearl, who lived to be 101 and outlived all 4 of her children and her husband, having lost them to HD. And you can kind of see in the corner, my mom is in the corner of the picture. And she lost her dad shortly after that picture was taken. And to be perfectly honest, after that time, HD wasn't really a big part of my life. Aside from, my dad was very much involved with the Huntington Society, so we'd have to go do the fundraisers and stand outside the liquor store with our box of apples. But other than that, I didn't really think much about HD, aside from learning about it in genetics class in high school and university. So I just went on to pursue my interest in science, and I went to the University of Toronto for graduate studies. And it was at the end of grad school that we learned that my mom had the gene too. And this came as quite a surprise because she was in her early 50s and showing no symptoms. So usually people tend to show symptoms, you know, mid to late 30s, early 40s, some people earlier, some people later, but we kind of thought we had gotten away from it, but we were wrong. And so at this point, I decided to change fields and pursue a career in HD research instead of cancer research. Now, there were only 2 labs in Canada at the time working on Huntington's disease. The Hayden lab in BC and the Ray Truant's lab in Hamilton. And so that turned out to be pretty lucky, because Hamilton is only a 45-minute drive from my hometown of Niagara Falls. And so I was expecting my first kid, and I was pretty keen to have help from home. So it was pretty lucky that there was an HD research lab so close by. So I went and interviewed with Ray Truant and started working in his lab after my first mat leave. And what the Truant lab is working on is they were studying, trying to understand what the Huntington protein does in hopes of understanding what's going wrong in HD. So I'm going to take a minute now, and we're going to dive a little deep into some science stuff. So if you'll stick with me for the next 5 minutes or so, and don't fall asleep, I want to explain a little bit about the Huntington gene and a little bit about the Huntington protein, and talk about cells because it will, everything I tell you about what we're working on will make a lot more sense. Okay, so don't go to sleep. All right, so here's your quick 5-minute biology lesson. So our cells have many different compartments, but probably the most important one is the cell nucleus, because that's where the DNA is stored. And DNA is important because our genes are made of DNA, and our genes are the blueprints for proteins. And proteins are what do all the jobs in the cell. So for our purposes, when we talk about protein, we're not talking about steak. I know that might be hard here in Alberta. But you really got to think of proteins as little molecular machines that carry out all the jobs in the cell. And so how this works is that from the DNA blueprint, a copy is made, which is called RNA. And the RNA goes out into the cell, and it gets translated into many copies of protein. Now the proteins come in all different shapes and sizes. And it's really the shape of the protein that dictates its function and how well it can do its job in the cell. So, for example, top left, there's a ring. That ring protein is actually a DNA repair protein. And it slides along the DNA strand and tries to detect any damage there. And if there's damaged DNA, which is bad, and we're going to talk about that a little bit more in the next slide, if it senses any damaged DNA, it recruits other proteins in and they fix it. We have a lot of genes and proteins dedicated to fixing our DNA. Okay, so proteins come in lots of different shapes and sizes. Their shape dictates their function. What about the Huntington protein? The Huntington protein looks like a big glob. It's a flexible glob, and its job in cells is really just to act as a scaffold. It interacts with other proteins and just brings them where they need to be to do their job. That's it. Now it's a very versatile, it changes shape and it interacts with some proteins over here to do this job, other proteins at a different time to do another job. And that makes it really hard to figure out what's going wrong in HD. Because what we do know is that, okay, so the Huntington gene, which is in the DNA in the nucleus, it has this region of CAG repeats. Everybody has a Huntington gene, and everybody has CAG repeats. But if you don't have Huntington's disease, you have maybe 18 or 20 CAG repeats. If you have more than 37, you will have Huntington's disease at some point in your life. And what happens is that expanded CAG bit in the Huntington gene gets translated to an expanded Huntington protein, which is in green here. And that just changes the shape of the protein a bit. And somehow, that change in shape of protein means that neurons die. How exactly? That's what we're trying to figure out. We don't know. But we do think that it has something to do with the role of that Huntington protein in the cell nucleus. Okay, so the rest should be clear as mud, right? So we got our first clue about how the Huntington protein does something important in the nucleus when we found that it moves to sites of DNA damage. So you can do this by zapping cells with a laser and damaging the DNA. So that's what I did in this experiment. I had cells growing in a dish. The cells are skin cells from an HD patient. We get patients donating their skin cells, and their sister who doesn't have the gene is the control, and we use these cells all the time. So I was growing them in the dish. I stain them with a blue dye that stains the DNA so I can see where the nucleus is under the microscope. So that blue ball in the black square, that's a nucleus. And then I take a laser on the microscope and zap a line of damage in the DNA. Give the cells about 20 minutes to recover, and then I looked to see what was going on with the Huntington protein. And it was really, to my great surprise, that I saw that the Huntington protein was lined up at the sites of DNA damage. This doesn't really sound like a big deal, but it was honestly the most exciting moment in my scientific career. I was sitting in this dark room on the scope, and I saw this, and I knew that I'm the only person in the world right now who knows that Huntington protein moves to sites of DNA damage. And at the time, we didn't know, how important that might be. But those moments of discovery are really what leads to bigger things. And as a scientist, that's like what we live for, because the rest is really hard. So that moment of discovery couldn't have happened if it wasn't for funding from the Huntington Society. Because the Huntington Society paid for the scope, the microscope that I used to do the experiment. So this is, this is the first example of where your money is going. Little discovery in a dark room. We went on to show that what the Huntington protein is doing there at those sites of DNA damage is doing its job. It's acting as a scaffold. So it brings in other DNA repair proteins so they can do their job. But the question was, is this actually important to disease? Because like I said, the Huntington protein does a million things. Which one is causing neurons to die? And so there were some clues. We knew that DNA repair was linked to Alzheimer's, Parkinson's, and a bunch of other neurodegenerative diseases. So we thought, okay, we're probably onto something. But then we got a major clue. So this came in the form of this very big study. It was published in 2015, and what this study was asking was, what's the difference between people who get sick early and people who get sick late? So, as I mentioned, some people get sick when they're in their 30s. My mom didn't start showing symptoms until her late 50s. We know one thing that affects that. So those CAG repeats in the gene that I mentioned, in general, the more you have, the bigger the expansion, the earlier you'll get sick. But there's a huge amount of variability. So one person with 42 repeats could get sick in their late 20s, and one person with 42 repeats could get sick in their 60s. So the question is, what's the difference? Because, yeah, we want a cure for this disease, but if we can just tap into whatever's happening there and just push it off by 20 years, that is fine. I'll take it, right? So that's what this study was asking. And so they looked at thousands of HD patients, and they looked at all their other genes and asked which ones are different in people who get sick early versus people who get sick late. And what they found was that most of those genes were involved in DNA repair. So then we got excited because we knew that the Huntington protein was physically going to sites of DNA damage, interacting with these other DNA repair proteins. So if those DNA repair proteins are the ones that are different between people who get sick early and late, they might be having a direct effect on a protein. So this is a big clue. And the reason it's so big is because it came from a very large study done in humans. So this information came from thousands of HD patients, so we know it matters to HD patients. We're not just looking at mice here. And that's really important. So that was all very exciting. But really, the best part came next. Laura's drug lead. So this is Laura, and that's Ray. Ray is very tall. We are all very small. It's really hard to keep up with him when he's walking down halls. And what Laura was working on was a completely different project. She wasn't looking at DNA repair at all. She was looking at a slew of natural products that maybe could be drugs, and just asking, what do these things do to the Huntington protein? And the one she found, the one that had the biggest effect on the Huntington protein, turned out to be a natural product of DNA repair. So it's actually a little tiny bit of damaged DNA that gets snipped out during the repair process, and our bodies, we produce it all the time. What she found was when she put this natural product onto cells, the Huntington protein changed its shape to look more like the normal protein. And when we gave it to mice that are engineered to have HD, the mice got better. So this was really the most exciting part. This is how I'm trying to finally get into my point. This is how money from these types of events help get us from a little observation in a dark microscope room all the way to the point where we have a drug lead. Now, this particular drug, unfortunately, wouldn't be a great drug for us. It gets broken down really fast, so it works in mice, okay, because they have little tiny brains and it can get into the brain. Not so much in humans, but we're already working with this company called Huntington. They're making similar compounds that should do the same thing but last longer in the body. And so this is how we went from tiny observation to a drug lead with help from money that comes from events like this one. So where do we go from here? Okay, so we now know there was always a lot of different directions to take to look at HD, and there still are. We're looking at DNA repair, but that doesn't mean it's the only thing to look at. And there are labs all over the world that are taking different angles on this. But we have now focused all of our effort on DNA repair. We're very excited about Laura's drug lead and the similar compounds coming out of myokinin, but we can't put all of our eggs in that basket either. And so we're taking a close look at what is going on with this process of DNA repair and how it's going wrong in HD. And hopefully next time I come here, because I'm coming back, hopefully I'll be able to tell you some more news. But the best place that we can look for this information is out of humans. Like I said, that big study that set us on this path. The reason that we could be so confident that we were on the right path is because the information came from humans and lots of them, and that's what we need. And once again, the HD community has stepped up. So if you're not, from an HD family, you may have never heard of this trial, but there's this amazing study going on. It's called Enroll HD, and there are over 16,000 people in this study. That is just, you don't get that in cancer research. You don't get that in Alzheimer's. This is the HD community coming together to do this. And what it is strictly observational. So, you go in, I'm in it. You don't need to know your gene status to be part of it. It's all anonymous. So I go in once a year and they do a bunch of tests and all that information gets logged. And now researchers can go through the data and ask the questions. We're going to ask questions about DNA repair. Other labs are going to ask other questions, and together we're going to figure this out. So I'd like to leave you with the sense that it really is an exciting time in HD research. We've got this big, huge trial, observational trial. We've got so Roche and Wave are two companies that are running the most advanced clinical trials we've ever had. And that's working to actually knock down the levels of the bad protein. Safety trials are done, so the next step is to actually see if it works. And this is those are only two of the trials going on right now, and it's incredible how far we've come. 10 years ago, there might have been one trial going on, and now, I don't know how many. Do you know how many trials there are right now? It's over 50. So it's moving very quickly. And I have to tell you, HD researchers really do believe that there's a cure for this. And there's a real urgency about them. So I've obviously invested because I'm from an HD family, but when I talk to people at conferences, it's not like cancer research was. Nothing against cancer researchers, they're great. But there wasn't that sense of urgency, and everybody's in it together on this one. So if you're interested in finding out the latest in HD research, this is an excellent resource, hdbuzz.net. It basically covers all the most exciting studies that come out in plain language. And I think that's all I have. So I just want to acknowledge all of our funding agencies. We get money from the Huntington Society, but from other places too, and without that, none of this could happen. So thanks a lot, and if you have any questions, please let me know.